This is the same house from the end of the last episode. The model sees 4 clues: 2,000 square feet, 3 bedrooms, its condition, and its location. Each clue passes through its own importance knob. Together, those knobs produce a predicted price of $412,000. The real price is $390,000. So, the prediction is $22,000 too high. Gradient descent can change a knob once we know that knob's slope. But now there are 4 knobs and only one final mistake. Which knob should change most? Which should barely move? Could 2 knobs deserve different changes even when both helped push the prediction upward? Pause and decide what you would try first. The most obvious idea is to lower every knob by the same amount. Let us lower each one by exactly 0.01. The 4 weights become 0.39, 0.19, 0.19, and 0.79. The prediction falls from 4.12 to 4.0925. In real prices, about $409,250. The loss falls from 0.0242 to about 0.01853. So equal change was not nonsense. It moved in a useful direction, but it treated 4 unequal relationships as if they were identical. Floor area did not affect this prediction in the same way as condition. Bedrooms did not travel through the model with the same strength as location. Equal correction throws away that information. What we need is not equal blame. In fact, the mistake does not literally belong to any knob. We need a separate sensitivity clue for each one. If this knob changed a tiny amount, how much would the final loss change? We already know one honest way to get that clue. Freeze 3 knobs. Nudge only the floor area knob. Run the entire prediction again and measure how the loss changes. Put it back. Now, nudge only bedrooms and rerun everything. Then condition. Then location. With 4 knobs, that is tedious but possible. And this numerical probing method is useful when we want to check our work. But imagine that the model has 1 million adjustable weights. A single training step would need roughly 1 million extra forward runs just to estimate their separate slopes. The method works in principle. The cost explodes in practice. Can we reuse the calculation the model already performed instead of rebuilding the whole prediction once for every knob? To answer that, we have to stop treating the prediction as one sealed box. The model stores convenient normalized versions of the house facts. 2,000 square feet becomes 2.0. Bedrooms stays 3.0. Condition is 0.6. And location is 0.9. Now follow the prediction forward. Floor area 2.0 multiplied by its importance. 0.4 contributes 0.8. Bedrooms 3.0 multiplied by 0.2 contributes 0.6. Together they form a saved space score of 1.40. Condition 0.6 multiplied by 0.2 contributes 0.12. Location 0.9 multiplied by 0.8 contributes 0.72. Together, they form a saved context score of 0.84. The final price stage has 3 more adjustable settings. They are not calculated from this house. They are simply the model's current starting values, just like the 4 earlier knobs. One knob, 0.4, controls how strongly the saved space score affects price. Another, 0.5, controls the context score. And a base setting of 3.14 provides the starting price level. 3.14 plus 0.4 times 1.40 plus 0.5 times 0.84 gives $412,000. Then the model compares 4.12 with the real value, 3.90. The error is 0.22. Half of that error squared gives a loss of 0.0242. The final mistake was not created in one jump. It was built through a chain of small relationships, and the useful intermediate values are already sitting here. Where should responsibility begin? At the only place where we can see the mistake directly, the final prediction. Our model says $412,000. The real price is $390,000. So the prediction is too high. Imagine giving the prediction knob the tiniest push upward. The mistake grows. Push it downward, and the mistake shrinks. That gives us both a direction and a strength. For this loss, that local strength is simply the gap. 4.12 minus 3.90, or 0.22. Don't treat 0.22 as a number to memorize. Treat it as a message. Lower the prediction, and this is how strongly the loss currently cares. Now we need to pass that message to the earlier parts of the model. Picture the 0.22 message copied onto two independent paths. It is not a fixed pile being divided up. The space score does not control the whole prediction. Its current multiplier is 0.4, so only 40% of a tiny space change reaches the prediction. On the space path, multiply that copy by 0.4. The result is 0.088 for the space score. On the context path, start again with the same 0.22 message and multiply by 0.5. That gives 0.110. The 40 and 50% do not need to add to 100. They describe two different connections. Each connection independently scales the same arriving message. We did not rerun the model, and we did not ask one connection to understand everything. We joined neighboring clues to make a longer path. Mathematics calls this the chain rule, but the useful idea is simpler. Carry the message backward, scaled by each local influence. Now, let the two messages fan out to every adjustable knob. You do not need to hold 7 calculations in your head. Watch the lengths of the responsibility bars. On the space branch, bedrooms receives a stronger message than floor area, because the bedroom input is larger here. On the context branch, location receives more responsibility than condition. The 3 price stage knobs receive messages too. The space multiplier has the largest bar of all. The context multiplier and the base receive smaller ones. Only now do we reveal the exact slopes. They are 0.1760, 0.2640, 0.0660, 0.0990, 0.308, 0.1848, and 0.2200. Do not memorize them. Read their pattern. Equal correction would move every knob alike. These bars say the knobs did not contribute equally, so they should not receive equal corrections. Each connection needed only 2 things: the message arriving from its right and its own local influence. Together, those local decisions assign responsibility across the whole model. Now, return to the graph that produced the prediction. Nothing has moved. We are simply reading the same relationships in reverse. The final loss gives the prediction one clue, 0.22. That clue is copied onto every backward path. It is never divided into a fixed total. One copy is scaled by the space multiplier, 0.4, and arrives at the saved space score as 0.088. Another copy is scaled by the context multiplier, 0.5, and arrives at context as 0.110. Those clues continue backward. Space reaches the floor area and bedroom weights. Context reaches condition and location. At the same time, the saved forward values assign responsibility to the two prediction stage multipliers, while the base receives the prediction clue directly. Watch the 7 gradient values land on the 7 adjustable settings. One mistake has now taught every weight, not through one global guess, but through a sequence of small local relationships. Replay the journey. The house values traveled forward. The model saved useful intermediate results. The final prediction produced one loss. Then a sensitivity clue began at that loss and traveled backward, one local connection at a time, until every adjustable weight had a slope. You already have the mechanism. Now we can give it its formal name, backpropagation, short for propagating these useful sensitivity clues backward through the computation. Backpropagation calculates gradients. A gradient is simply the collection of one local slope for every adjustable weight. Backpropagation does not change the weights. Gradient descent uses the gradients to make the controlled changes. Calculation first, correction second. Let us reunite the two ideas. With a learning rate of 0.1, gradient descent subtracts 1/10 of each calculated slope. The floor area weight changes from 0.4 to 0.3824. Bedrooms changes from 0.2 to 0.1736. Condition changes from 0.2 to 0.1934. Location changes from 0.8 to 0.7901. The space multiplier becomes 0.3692. The context multiplier becomes 0.48152. And the base becomes 3.118. Now run the model forward again. The new space score is 1.2856. The new context score is 0.82713. Using all 7 updated settings, the new prediction is about 3.9909, roughly $399,092. The error falls from 0.22 to about 0.0909. The loss falls from 0.0242 to about 0.00413. The earlier equal change to the 4 visible knobs reached a loss of about 0.01853. Updating those same 4 with their gradients reaches 0.01408. Updating all 7 adjustable settings reaches about 0.00413. Each companion says the same thing. Separate influence clues make a more informed step. The code now mirrors the picture. First, the forward pass computes each contribution, saves the space and context scores, produces the prediction, and measures the loss. Next, the backward pass starts with prediction minus truth, 0.22. It combines that arriving clue with each local multiplier, moving from right to left. The results are the 4 gradients. Then, and only then, the update step subtracts the learning rate times each gradient. Finally, the changed model runs forward again, so we can check what actually happened. Forward computes values, backward computes sensitivities. Gradient descent updates parameter. The full training step needs all 3 jobs, but they are not the same job. Our house model has only a few stages. A deeper model may contain dozens, hundreds, or far more. The total calculation becomes large heteroexynist, and keeping it stable becomes harder. But the local rule does not change. Each stage receives a useful clue from the stage after it, combines that clue with its own local influence, and passes the result farther backward. This efficiency is why one final mistake can teach an enormous collection of weights without separately nudging and rerunning the model for everyone. But efficient calculation does not guarantee an easy learning problem. Across many stages, the multiplied clues can shrink until early weights receive almost nothing. They can grow until updates become unstable. And the method can faithfully optimize a loss that measures the wrong real-world goal. Backpropagation gives us gradients efficiently. It does not promise that the gradients are healthy, that the objective is wise, or that the final solution is globally best. Before we finish, rebuild the idea without its formal vocabulary. Follow the model forward and save the useful intermediate values. Measure one final mistake. Start where that mistake is visible. Ask how a tiny change would affect it. Move backward through the same stages, combining the arriving clue with each local influence. Collect one slope for every adjustable weight. Use those slopes to take a controlled downhill step. Then, run forward again and check. That backward calculation is backpropagation. The connected multiplication is the chain rule. The collected slopes form the gradient. The controlled parameter change is gradient descent. Now, transfer the structure. Imagine a model estimating delivery time from distance, traffic, weather, and depot workload. The clues and stakes change, but the mechanism does not. Values move forward to create one estimate. Responsibility clues move backward to calculate how each earlier weight could affect the final loss. We can now teach many weights from one mistake, but our small house model still depends on humans to invent useful intermediate ideas such as space and context. What kind of model could learn useful intermediate features for itself? If this is how you want to learn AI, subscribe and join us. Like the video, so more curious minds can find the series. And tell us in the comments what clicked, what was unclear, and what we should improve. Your feedback will shape the episodes that follow.